All right, so the things to go over. Capacitors. They're charge storage devices. They got tons of applications all over the place. One of them is the defibrillators. All right. So you pump like 20 amps of current into the chest cavity for a fraction of a second. So you get to control the amount of current that you want to deliver, meaning that the amount of charge that you want to deliver is highly controlled and the duration is highly controlled. For you to be able to do that, you need to be able to store this amount of charge somewhere. All right. So the charge gets stored inside these capacitors. And once again, you got the flash photography. You can control the discharge time. It's 2,000th of a second here, and this is 0.3 microsecond, millionth of a second. Here. All right. So obviously, there's a couple of things involved regarding capacitors. Number one, they're charge storage devices. They need to be charged up. That's going to take time, and they need to be discharged, and that's also going to take time. So you kind of control the charging period and then discharge period. Okay, how it is done is going to be one of the future lectures. All right, so let's just talk about capacitors in general this week, and that's what we have done in essence. All right, so the capacitor is a charge storage device. So the first thing you need to do is you need to charge it up. And how do you do that? You hook it out to your battery. You hook it up to your battery. So that's what we do. All right, so there's a switch. You throw the switch on. It's just going to charge on, and then obviously you can also discharge it. All right, so you can charge it up to the potential supplied by the battery. All right, so the potential difference between these two plates is going to be the same as the potential supplied by the battery itself. So the electronic symbol of a battery is this. This is your voltage source, the power source. All right, so the positive terminal is going to make this side positively charged. The negative terminal is going to make the opposite side negatively charged. All right, so it's going to acquire a net charge, positive or negative. It's going to be the same. So it's going to have equal amount of positive and negative charges. So the amount of charge that you can store is going to depend on the voltage supplied by the battery. And it's also going to depend on the capacitance of a capacitor. All right, so capacitance of a capacitor. So the larger the capacitance is, the more charge you're going to be able to store in. All right, so you can turn this into an equation. So it's going to give us the equation, which is Q equals C times V in essence. Now, capacitance depends on the geometry in essence. So it's going to depend on the size of the area of the plates. It's also going to depend on the separation distance between the plates. All right, so closer these plates to each other, the larger the capacitance is going to be. All right, and you can turn this into an equation by multiplying everything with a proportionality constant, which happens to be epsilon naught in this case. All right, so how we attain this equation is called the derivation. All right, and every single derivation is going to be done the same way in problem solving. In a problem which is involved, is going to require the same resolution, same way, same approach in these capacitor problems. All right, so here's the generic equation for capacitors. So this is the amount of charge that you're going to be able to store inside a capacitor. It's going to depend on the capacitance, and it's also going to depend on the voltage supplied by the battery. All right, so the first thing you need to do is you need to isolate C on the left-hand side. And on the right-hand side, you will have to do a bunch of back substitution. So the voltage represents the amount of energy stored in the electric field between two opposite charge regions, which are separated through a distance d. That's it. All right, so this electric field is going to depend on the net charge. All right, so the electric field lines start from the positive charge region. So it's going to depend on the net charge inside the capacitor. All right, so the net charge inside the capacitor is given by this one. All right, so if it's a flat conductive material like a sheet of metal. All right, so the net charge is going to be uniformly distributed on it. We came up with this equation using the Gauss's law. All right, so we do a back substitution. Immediately, you end up getting cancellation, so Q's will cancel. A denominator of a denominator is a numerator, so just pull it up, and that's it. So we came up with an expression for the capacitance, which is geometry dependent. All right, so this was straightforward. Okay, so this is the way you will do every single problem that requires capacitance. All right, so if you're looking for the capacitance of any geometry, basically you step through it this way. All right. All right, so we got two parallel plates. They're going to be charged up using a battery. All right, so this is, once again, is going to represent the amount of charge stored inside a capacitor, which is going to depend on the voltage supplied by the battery. And you can charge up the capacitor until the voltage difference within the capacitor is the same as the voltage supplied by the battery. And C is going to represent how much charge it can actually store. All right, so that represents in essence. So voltage, once again, in terms of volts. C is going to be expressed in terms of farads, capacitance, and Q is going to be the net charge. It's going to be expressed in terms of coulombs. All right, so far, these are the only useful formulas that we got. All right, so you need to know the general expression for the charge stored inside a capacitor. Understand that the capacitance depends on the geometry. The voltage is the amount of energy stored within the electric field within the gap of two opposite charge regions, which are separated for a distance d. And then the electric field within is due to the net charge on each and every single plate, which is uniformly distributed in essence. All right, so those are the things that we got. Capacitor is also an energy storage device. All right, so there's a voltage difference, meaning that the energy is stored within the electric field. There's a voltage difference that implies that there are two opposite charge regions. So the energy is stored within the electric field within this gap, separated through a distance of r or d, depending upon the formula. All right, so that energy stored within the electric field represents the voltage or potential difference between these two regions. And if you place a charge within, immediately the charge is going to become energized. So now the charge has potential energy. If that charge is free to move, that potential energy is going to get converted to kinetic energy. All right, so we know that the capacitor is not only a charge storage device, but it's also an energy storage device. All right, so how much energy is stored inside a capacitor is given by these two formulas. All right, so the first formula is going to tell you about the stored energy in terms of voltage. The second formula is going to tell you about the stored energy in terms of charge. All right, so the voltage is related to the amount of energy stored inside the electric field, obviously. And obviously, this is also a charge storage device by virtue of the fact that it stores charge, it's also get energy. All right, so that's the meaning of it. So those are the two formulas that we'll get to use depending upon what's given. All right, so there's one more expression about where the energy is stored inside a capacitor. Where and how the energy is stored inside a capacitor. All right, so number one, it's going to be stored within the volume of the space between two opposite charge regions, and it's going to be stored in the electric field. So the amount of energy stored within this volume is known as energy density. All right, so the energy is going to be stored within the electric field, and it's going to be stored within the volume between these two opposite charge regions, in essence. All right, so this represents the amount of energy stored inside the capacitor, obviously. So when you do, and C depends on the geometry, so we'll do a back substitution. And the V in this case represents the voltage difference or potential difference. So that depends on the amount of energy stored within the electric field within this separation distance. All right, so you do cancel the like terms under the circumstances. And so area of the plate times the separation distance is going to give you the volume. So we'll do a back substitution again. All right, so when you divide both sides by the volume, it's going to give you the energy density. So that represents the amount of energy stored per volume. So what does this equation represent? What this equation represents is the fact that the energy is stored inside this volume within the electric field. That's what it means. So that's one of the equations that we will get to use time and time again in the future. So it's good to get back to it. All right, so if you place a dielectric material inside the gap of a capacitor, it's going to have a number of effects. Number one, dielectric material is an insulator. It's going to get polarized. And as soon as it becomes polarized, obviously, the induced electric field is going to be opposing the original electric field. So the sum of electric fields is going to result in a reduced electric field strength. So it's going to reduce the electric field strength. All right, so the dielectric, placing a dielectric inside a capacitor is going to reduce the overall strength of the electric field within the capacitor. So that's what happens. So here's the original strength, and here's the final strength. Notice that the final strength is actually smaller than the original strength of the electric field. All right, so if the electric field goes down, obviously the voltage difference is going to go down as well. All right, so I'm just going to step through this. All right, so this is the net charge stored in a capacitor. Here's the original capacitance. Here's the original voltage. All right, so which time the net charge is constant because the capacitor is separated from a voltage source, in this case, the battery. All right. So when you place a capacitor within, when you place a dielectric within, the voltage is going to go down, right? which means the capacitance is going to go up. So the net charge is constant. All right, so I'm just playing with the concept. So, so as soon as you place the dielectric inside, it's going to increase the capacitance, and it's going to reduce the voltage. So, which means that now it's going to be able to hold more charge. Capacitance goes up. As a result, it's going to be able to have more charge. All right. Here's what I'm talking about. This time, I will hook this onto a battery. So it's hooked onto a battery in this case. So which means that the voltage is going to be constant. And then as soon as I place the electric inside, the capacitance is going to go up once again, and the charge is going to go up. So it's going to be able to store more charge in it as soon as you hook it onto a battery, in this case. So it's going to increase its charge. So strength of the electric field is going to go down. The voltage is going to go down. Capacitance is going to go up. And the amount of charge you're able to store is also going to go up. All right, so capacitors can be connected in parallel as well as in series. All right, so when they're connected in parallel, the voltage difference across each and every single capacitor is going to be the same as the voltage supplied by the battery. All right, so the voltage difference is going to be the same. The amount of charge is going to depend on the capacitance of each and every single capacitor. All right, so the charge stored on each and every single capacitor is going to add up to the charge supplied by the battery. So this comes from the conservation of charge. All right, so I'm just going to skip the details on this one. The only thing you need to know is the total capacitance is going to be the summation of all the capacitances of a capacitor in this case. All right, so that's it. That's the only thing you need to know. So conceptually, all right. Then there's a point that I want to make. All right, so it's a tough point to make. I don't know the formula, so let's move forward. All right, so when they're connected in series, just like that. So the voltage supplied by the battery is going to get split across each and every single capacitor, depending on the capacitance values. The only thing which is of importance here is originally when this setup is hooked onto a battery, all right, so this plate is going to become negative charge. This plate will become positive charge. Everything in between, the region in between is actually neutral. So what's happening is there's a charge separation that you see here. This happens because of polarization. All right, so you pull this charge from the battery, you pull this positive charge from the battery, and everything in between happens because of polarization. So plates will become oppositely charged, or they will be oppositely polarized, and that's it. All right, so the net charge on each and every single plate is going to be identical. All right, so that's the only thing regarding this. All right, so a couple of things regarding this. All right, let's see on the derivation on this one. So the voltage supplied by the battery is going to get split across each and every single capacitor, depending upon the capacitance values. And we are looking for the total capacitance in this case. All right, so the voltage supplied and the voltage across each and every single capacitor summed up will be the same. So this comes about because of the conservation of energy principle. All right, and we'll come up with a generalized expression for voltage. So net charge divided by the total capacitance. All right, so the charges are the same in each and every single capacitor. So we just pull that term out. And so this is the reciprocal of the total capacitance that you're looking at, which is this term. So when the capacitors are connected in series, total capacitance is going to be computed by summing up the capacitor values reciprocally. So you're computing the reciprocal of the total capacitance. So this is going to reduce the overall capacitance. For the multiple choice section of the task, all right, look at problems like this. All right, so how do you combine these capacitances to look for the overall capacitance in essence? All right, so these are the problems that I want you to focus on. On top of that, I'm going to draw your attention to some other problems. All right, so this is the book that I'm using. It's Halliday and Resnick, because this is the book that we were using when I was an undergraduate student, considered to be the Bible of undergraduate physics at this level. Still one of the best books, not necessarily the best one in the market. Like I said before, my recommendation is just get a book. I found this online. It was free. All right, so you can find a university physics book online. Any university physics book will do. And it's everything that I'm teaching is standard physics, guys, despite the fact that I come up with my own examples and this and that. All right, I have a conceptual approach. Obviously, these physics books don't quite have the same rigorous conceptual approach, but the derivations and everything else, these are from these books in essence. Okay, so the things to focus on. I want you to find problems similar to the following. All right, so, and these are once again standard physics problems. Okay, so just get a book just like that. Go over some of the examples or most of the examples while you're getting ready for the multiple choice section of the class. It says view all the solutions here, which means that these guys are trying to, they make the book available free of charge. They want you to buy the solutions from them. All right, so that's what these guys are trying to do. These are the old editions, so it's not a big deal. You can find these solutions just about anywhere. Not a big deal. All right, there are a bunch of physics videos available online taking you through the solutions of these problems. The sort of stuff that I want you to focus on is like problem number 48. All right, how would you solve a problem like this? Okay, so for the multiple choice section of the test, notice that you got this capacitor, and it's got two different dielectric materials inside. All right, so what is the capacitance of a dielectric? What is the capacitance of this capacitor when you have two separate dielectrics, for example? Now that's an interesting question. All right, look for the solution. If you can't figure this out, just look for the solution. The solutions are a dime a dozen for this sort of stuff. They're literally video solutions. People solve this problem and post them online. Problem site. Another one is this one. This one is cute. Once again, you got two dielectric materials. All right, and notice that they're placed on top of each other. All right, so that's also cute. And then you got this 50. Now you got three dielectric materials, and the setup looks like that. All right, so how do you do setups like that? And so for the multiple choice sections of the test, hopefully you're not going to get anything this extreme, but this is the sort of stuff which is good to know. All right, and you may have a question like that in the multiple choice. They're not that difficult to solve, but just look for solutions for things like that. All right, and then you also have the obvious stuff. Look, you got this kind of setup. What is total capacitance? You got this kind of setup. What is the total capacitance? It's like a pick and choose problems. These are like everything that you see here is a standard physics problem. All right, so I don't want you to practice it so much that it becomes muscle memory. Just do enough so that you know how to do this sort of stuff. All right, so you need to be able to use some circuits, and you need to be able to do some of that stuff. All right, so this is the sort of stuff that you will need for your engineering classes, in essence. All right, so let's get back to physics. All right, so the stuff that I need from you guys is the next two. All right, so we did the review, so let's move forward. How do you figure out the capacitance of a cylindrical as well as a spherical capacitor? All right, once again, these are standard physics problems. All right, you will find the solutions once again in just about every single physics book. Let's get back to algorithm lesson. And standard physics books, capacitance. All right, you would normally find this early on. Okay, so here's a cylindrical capacitor, and it goes on and on and on. And here's the net charge, blah blah blah. It's got its own way of doing it. And here's the one for a spherical capacitor, the Parallax capacitor, and this is a cylindrical capacitor. Here's a spherical capacitor, isolated spherical capacitor. This is the earth that we're in. All right, the difference between the way this book does it and the way I do it is mine is much more structured. All right, I utilize the concepts much more effectively. Mine is much more intuitive than these books. Usually, it's called practice, obviously. All right, because eventually you find a way to express things. My way of doing it is exactly the same as the first derivation that I gave you. All right, it's understanding based. All right, so it's understanding based, and I'm using mathematics as mathematics. It's a mathematical tool, but the rest of it, it's just physics. I use mathematics as a language. All right, so you can find these derivations anywhere you want, but you're going to be forced to explain it regardless. So you might as well do it my way. That's what I'm saying, in essence. Okay, because mine is intuitive, and if you understand the concepts, it just works out. Okay, so you don't need a book for this sort of stuff, in essence. But if you want to use a book derivation, of course, you just go right ahead. It's a little bit more time consuming to do it that way. All right, so this is a capacitor because you have two absolute charge regions. Inside is positive charge, the outside is negative charge. Radius of the positive charge region, the radius of the negative charge region. So we're looking for an expression for capacitance, so which means that it's going to depend on the geometry. And then I place my Gaussian within that region. All right, so the Gaussian is going to help me come up with a mathematical expression for the strength of the electric field. All right, so you start off with the generalized expression for the amount of charge stored inside a capacitor, and then just isolate C, the capacitor. Okay, so net charge is net charge within the capacitor. So the voltage expression is the one that now we will have to focus on because the voltage depends on number of things. It's going to depend on the strength of the electric field within this gap. All right, so here's the generalized expression using calculus. So the gap is between this surface and that surface. So the surface is at the radial distance A, the second surface is at the radial distance B. So electric field is pointing radially in that direction. So you're just adding these contributions of the electric field along the radial direction. Now, for us to be able to do the integral, we need to have an expression for the strength of the electric field within this region. So that's where the Gaussian comes into play. All right, so by using the Gauss's law, you know that this electric field is going to be due to the net charge within this area. So this area is the area of a cylinder. And then we're only interested in the site area, obviously. So it's going to be 2 pi r times L. All right, so you end up using R, guys. This is the area of a Gaussian surface, so don't confuse it with the area where the positive charge is distributed. All right, so we end up getting a mathematical expression for E. So we just substitute into the voltage equation, and the variable is R. All right, so dr over R. If you integrate it, it's going to be ln of R, natural log of R, which needs to be evaluated between A and B. All right, so this is straightforward at this point. So you can factor out ln, so it's going to be d over A. All right, so do a back substitution into the voltage equation, and then the voltage equation is going to get substituted into the original capacitance equation. And then the charges will cancel. Denominator over denominator is a numerator. All right, guys, so you come up with a generalized expression for capacitance. Okay, so this is so much easier than the blah, 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 this what counts. All right, so cylindrical capacitor. All right, so it talks about the parallel plate capacitor and then trying to set up the meaning of the voltage. We already did last week. And it's already got some kind of an electrical field expression, which is from the Gauss's surface, okay, from 2 previous chapters. All right, mine is just much more compact. All right, it's just you set it up and you just follow the mathematics, back substitution after back substitution. And then you come up with this equation. It's cleaner, it's much more sensical, and it just works out much better. All right, it just comes out of literally your conceptual understanding. And the rest is, the math is just muscle memory. There's nothing there. Okay, so if you have a spherical capacitor, and this is the one that we looked at, once again, it's the same method all the way through. All right, so the way I set it up, I set up the derivation is, once again, it's logical. All right, it requires no book whatsoever. Once again, you got a positive charge region, negative charge region, set the capacitor. All right, so isolate C, go after V. V is the amount of energy stored within the electric field within this gap, the separation distance between this sphere and the next sphere that you're looking at. And you can figure out the strength of the electric field using the Gauss's law, according to which the electric field is going to be due to the net charge within. Area is the area of sphere, so you do a back substitution, which is going to be 4 pi r squared, so do a back substitution. All right, isolate E. All right, so substitute this back into the voltage equation, potential difference equation. For simplification reasons, I don't want to carry these terms, so this is the generalized K, the strength of the electric field. All right, so it's a simple integral, so this is going to give you negative 1 over R. Okay, so this section integral. Do evaluate it at the limits and then do a back substitution. Okay, but before we do that, I'm just cleaning it up. All right, so distribute negative, and then, all right, I'm just going to do a back substitution at this point. And then do a back substitution into the capacitance equation. And then I'm probably going to express K as is if it up to. All right, so this K was 1 over 4 pi. All right, so I'm having a common denominator. And then I'm expressing K explicitly in terms of epsilon naught. All right, so this is the generalized expression for capacitance for a cylindrical capacitor. All right, notice that the book came up with the same. All right. And then if it's an isolated sphere, just like the Earth, then obviously take this second sphere and place it at infinity. All right, so factor out B. There's going to be a cancellation between this B and that B. And then when the limit goes to infinity for B, it's A divided by infinity is going to be 0. All right, so it gives you a generalized expression for that, which happens to be this. All right, so you guys have to practice and practice, practice. So these two derivations need to be practiced. All right. In terms of short work problems, okay, these are the only two things that I can ask you. I can ask you only variations of these two.